This is my experiment in a digital phase lock loop frequency synthesizer using the MC145151-2 integrated circuit. The reference frequency is provided by a 1.8432 megahertz crystal oscillator. The VFO is a Varactor-tuned Hartley oscillator between the frequencies of 4.1 to 4.5 megahertz. I've also implemented a lock detect LED, and the whole system runs on 9 volts. The 1.8432 megahertz oscillator is divided by 1024, providing a reference frequency of 1800 hertz. I also experimented with a 2048 divider giving 900 hertz and the 512 divider giving 3600 hertz, but the 1800 hertz turned out to be the most convenient for this demonstration. The 4.1 megahertz divided by 1800 hertz gives a count of 2278, and the input is the binary input. The phase lock loop chip has a 14-bit divider input to provide the selected frequency. The 4.5 megahertz divided by 1800 has a count of 2500, and the input is the binary, again, that binary number that's on the input of the chip. The 4 lower frequencies are the ones I'm going to use as demonstration. I needed to find a reasonable count that I could just select a single bit to change the frequency. The inputs have internal pull-up resistors, so to select a frequency I tie one of the pins to ground, and that changes the count. So the four counts that I'm going to try are 4.489 200 megahertz, 4.487 400 megahertz, and the bits I'm going to tie to ground in sequence to test those frequencies. The output frequency I actually see is a little bit higher than the calculated frequency. I think that's because the Hartley oscillator isn't very clean. I could put a low-pass filter to tighten up that frequency, but the Hartley oscillator doesn't have much of an output. It's kind of marginal for the chip. The chip requires a minimum of 500 millivolts peak to peak, and the Hartley oscillator's output's about 700 millivolts peak to peak, so there's not a lot of room to add a low-pass filter there. The crystal oscillator output is 1.3 volts peak to peak. There's plenty of overhead for that, plenty of tolerance for that. Okay. There's also another reason for the frequency being not very tight is the fact that I've implemented this on my prototype board, which has a 9-volt regulator here. This is the crystal oscillator circuit, and over here you have the Hartley oscillator circuit with the Varactor tuning here. The green LED is the lock detect LED, which is useful for diagnostics. It made it easier to figure out what was going on if you can see it actually working with the lock detect. So the antenna, the green wire, is like a short antenna that couples the signal into my shortwave receiver, so I can see what get a reasonable idea of what the frequency output is. So let's get this guy turned on. Turn on the receiver. I'm going to start at the 4.489, and you can hear the signal in the receiver. So the first bit that I'm going to hit is a little bit lower. So the calculated value is 4.489,200, and I've got 4.93, 4.9. When I get to 4.89, it's already at the lower end of the range of the oscillator. But it seems to be centered more at about 4.9, 4.91, 449 to 4491. 4491 seems to be more reasonable at the center. So it's a little higher than the calculated value. The next bit down should be 1800 hertz, different from that. And this is the reason I didn't do the 900 hertz one. So this one should be around 4.487. It's 4.488. It's not too bad. It's pretty close. But it's about 1800 hertz lower than the first one. Now the next one I'm going to jump a few bits over to 4.433 megahertz. And let's see how that works out. Is it working? Oh, 4.433. I went too far. There it is. 4.437. It's saying it's a little bit higher than it should be. But it's, again, the Hartley oscillator isn't very clean, so it has a lot of harmonics in it. And the last one is 4.231. This one I have to go down quite a bit. 4.2. It's not there. 4.231. Did I make a mistake? Oh, there it is. That one's off quite a bit. 4.26. I'll have to check on that. Miscalculated. Yeah, 4.232. Now this one's off quite a bit. I'll have to go back and check that again. But you can see that it's, and you know that that's the signal. That's the signal, and you can kind of see the LED flicker a little bit when I change the frequency over. And I'll see if this goes back to 4.433. Yeah, this is the 433, 437. And then 4487. 449. And there's the 4 point is the next one up. These two are right next to each other, these two channels. So they tend to be about the same frequency. This 4489, and this should be a little bit higher. 4.491, so it is about 1800 hertz higher. I'm kind of surprised at that lower one. I'll have to look at that. But it's, you know, it's working. And it is a prototype circuit, so this is a kind of a test circuit. So let me see if this one goes to 4433. Yeah, there it is. It's higher than it should be. Again, probably something to do with the Hartley oscillator not being exactly right. And then this one is way down, so it seems to be higher by some percentage. 4230. This turned out to be 4260 or so. It's calculated values for it around here somewhere, but it turns out to be up here, right there. Let me write that down. $42.63. Okay. Okay, I'll have to look at that later. But that's basically the operation of a digital phase lock loop. This would require a bit more development before I could use it for anything, and I'd have to clean up the Hartley oscillator and probably tune the crystal oscillator better. Go back to 4489, 4491, I think it was. Yeah, there it is. So it's consistent. And it's off. So that's a quick demonstration of my my experimental circuit for the digital phase lock loop.